Okay, so welcome to the last lecture in machine learning. During this journey, we have been exposed to fundamental machine learning concepts from supervised to unsupervised learning. We also had looked at briefly the dimension reduction techniques. And this is just a brief reminder, a brief recap before we hit the last part, which will be about ensemble learning. Okay, so if you guys remember, in dimensionality reduction, we have seen two key methods, right? So we saw feature selection methods and principal component analysis for feature dimension reduction. And also we saw clustering, okay? Now, if you think of clustering, I know in the previous lecture I did not mention clustering as a dimension reduction technique, but you can also think of it as a dimension reduction technique. What we are reducing in this case, it's not the number of features, it's the number of samples, okay? So let me explain and just remind you. So given here, let's say we have n samples, okay? And we have d features right here. So here I flipped the matrix, but it's fine, so it should be okay. So what we have, we will, for the feature selection method, we will learn how to select the most important features. So here we reduce the dimensionality of the features from 1, 2, 3, 4, 5, 6, from 6 to 2. Okay, so here each sample X belongs to R6, and here each sample belongs to R2. So this is a lower dimensional space. Right, now for PCA, interestingly, we are not extracting features. Well, we are not, selecting features, we are extracting new features. And this is why here you have a different texture for these two features, because these two features are not selected from the original set. So since we are projecting the data onto new directions, we somehow cannot directly track the original features. So basically, we simply project the data, if you guys remember. So we simply project the data onto the principal component axes, and then the projected samples, okay, features here. So we have new features. So in the original space, these new features right here, for example, in this case, we have 2 dimensions. They are newly extracted features in the new space. So here we extracted new features. So let me know, extracted new features. Okay, so for clustering, what we have n samples and d features, but by learning how to group similar samples together, and for example here we have 2 groups, then for each group we can represent it in some clustering algorithm. We can, like, for example, k-means, okay? We can represent each group by the average, somehow the center of the group. So what we call the centroid, okay? Sometimes we call it also clustroid. Clustroid is a point to cluster, but the commonly used term is basically centroid, okay? So here we have reduced the dimensionality of our input samples. So we went from here, how many samples? 1, 2, 3, 4, 5, 6, 7 to 2 samples. So we have reduced the number of samples from n equals 7 to n prime equals 2. Okay, so you can think about it as what? As a sample reduction algorithm. So here, let's, like, color those accordingly. So which algorithms can be supervised? Guys? So feature selection method can be supervised. Okay. Clustering, no, unsupervised. Very good. And PCA is always unsupervised. So these two are unsupervised. Feature selection method can also be unsupervised. Okay. Now, for which methods are used for feature dimension reduction? So it's the feature selection method in the PCA. And for the simple dimension reduction, it's basically clustering. Okay. Great. So previously, we have seen different algorithms for, so why we're using dimensionality reduction. There are many reasons, many applications. One of them is to visualize data, analyze data, discover hidden patterns in data, and also boost the performance of supervised learners like classifiers and regressors. So here, like in classification, we looked at, let me just, base classifier, SVM, support vector machines, soft perceptron, and different types of perceptrons, if you guys remember. And we have also KNN classifier that I will explain right now because it's one of the fundamental and basic classification algorithms that we did not learn about, so I'll just cover it here. And for regression, we saw linear regression and nonlinear regression, specifically the sigmoid nonlinear regression model. Okay. Now for KNN, what is KNN? What does KNN stand for? The K is like just the number of it's just a variable. Okay. Number of samples that we will select, or neighbors. N is nearest, and the other N is neighbors. So the basic idea of KNN is that we have our training samples from two classes. So these are my training samples. Okay. And I have another class, let's say this class. And then given my training data, I have new points, and I don't know, these are my testing samples. So here I have two testing samples. I don't know how to classify them. So what KNN does is basically, let's say, for example, if this point is in the right space, like right there, what KNN does is, like, for the testing sample, it computes its distance to all points in the data, all those points, okay? So I compute the pairwise distance between the testing sample and each training sample, and then we will select what we call the K nearest training samples to the testing sample. So here, let's say K, we fix it to 3. So the K nearest samples to this one is these 3 guys, okay? Then the next step would be how I'm going to label my new testing sample. It's very simple. I look at the majority of the labels of my K nearest neighbors. So here all of them are green, so I'm going to label this one as green, okay? Now if I have, for example, let's say a point right there, maybe. So this is a second testing sample. So this testing sample, I compute also the pairwise distance from this testing sample to all other training samples. And I pick the top, let's say the top 3. I'm going to just move this a little bit down. Okay, it's not moving, it's okay. So the top 3 closest neighbors. So let's say maybe these 3 points, okay? Now the majority label, the most frequently label is yellow. So this one will be tagged or labeled as yellow, so it will belong to the yellow class. And this is the basic concept of KNN. Now I have a question for you. Do we need cross-validation for this one? How does it work? So will we need to use cross-validation for this one? If I have a new testing set, right? For example, if I want to classify, okay, let me just ask an easier question. Do we need to train a model here? No, very good. So we don't need to train a model, right? So it's very straightforward. You have your old data, you just compute the distances, rank the distances, okay, by decreasing order, select the top K points with the smallest distances. Okay, great. Now, this is, so basically these are the supervised learners that we learned about, and this is how generally the framework works. So what we have for whether we have a regressor or a classifier, this is what we call the predictive learner that we want to train. So first we have our input data, the training data X, its corresponding training labels or scores in regression. So we give all this to our model to train it. We train our model, and then in the next step we will test it. So to test it, we have our separate hidden data set, okay, the X test. then we pass it through the model to test it, and then after that we get basically the predicted scores or labels. So this is, the typical framework of a supervised learner. Now, what are the disadvantages of relying on a single learner? There are, many, but the most important or relevant ones are those. So basically, here we only rely on a single model, and a single model cannot know it all. Okay, you just, if your model performs well, it's good, it's all right. But if it performs weakly, then you're in trouble. Okay, relying on a single learner might not be a good strategy to optimize or even to build your company. You don't want to recruit a single expert. You want to recruit a bunch of experts. Okay, so this is one thing. So single model, it might be prone to errors. And the second one, when a classifier is stuck, when your model is stuck in the local optimum, it might not perform well. Okay, but let's say you recruit a bunch of learners, a few of them get stuck, but many of them do not get stuck. So they just, find the right solution. Then if you take your information from all those, learners, ultimately you will not get stuck. Okay, so this is, kind of the intuition behind ensemble learning. So ensemble methods, they have many, how do I say, we can call them in different ways. So we can call them like the multiple learner systems, committee of learners, you have mixture of experts, learner ensembles, ensemble-based systems, learner. So here a learner, but by a learner we mean a classifier or a regressor. Okay. So so this is an example of how an ensemble learning method works. So in the beginning, let's say what we have our training data, okay, TR. This is our training data. So the data we will train each of these models. So we have an ensemble of learners. Model 1, so this might be a support vector machine, maybe random forest, okay, another model, or it can be the same model but trained differently. So I'll give you more examples. So here we have our training data. We take the training data, we pass it through each of those models independently. So each of those models get trained independently. Okay, they learn their the optimal decision boundary, for example, for that particular data set, and then ultimately, when we want to test our data, so we're gonna have now the testing samples. So these are the testing samples. So now test set, and here what we will do in the testing stage, you will simply pass the data through all those models, and then get ultimately a prediction. Okay, so it will pass through these, and one by one you'll get different votes. So for example, in this case, how many samples we have, how many testing samples we have M samples. Okay, so each of those models, if I zoom a little bit, each of those models actually will predict a Y tilde for model 1. Okay, and here the dimensionality is M, of course, M predictions, and we'll have another prediction vector Y2, okay, by model 2, and by the final model K. So YK tilde, this is the prediction, okay? Now the last step, which is also an important step, how are we going to aggregate these predictions together to ultimately get the final predicted output? So this is, there are different strategies to do that. Okay, but this is one key step to think about it. So once we train the models, we test them independently in this case. They will have different outputs. How are we going to merge those outputs? Okay. Now, once we have our models, let's say, for example, from now on, I'm going to talk about classifiers without loss of generality. So which means that this also can be applied to regressors. Okay. So diversity of learners is very important in ensemble learning techniques. And what diversity means, well, there is no consensus on how we accurately define the diversity of a classifier, like a set of classifiers, okay? But we can say that classifiers, a simple definition is like a class of classifiers or learners are diverse if their decision boundaries differ from each other. And if you were to build an ensemble of learners, you want them to be diverse. You don't want to learn from basically a cloned version of the simple model. Okay, otherwise you'll be learning the same thing. So let me explain. Let's say this is this is our data, and here we have two variables, or two features. Okay, we can call them also observations. So let's say I have a first model. I train a first model. Maybe I have two models. Okay, so here my first model will give me a boundary, a decision boundary around there. So this is model 1, and then I have another model, and the model 2 will give me something around here. So these two models, their boundaries are very close. So this is problematic because if you were to put a point right there, okay, maybe right here, it's very difficult. You don't know whether you classify it. Okay, I'm going to put it like this. Okay, here you're going to classify it as probably a circle, okay? But it might not be a circle, it might be a cross because the boundary is not well captured, okay? Through these two models. By both models, this point will be classified as like an orange circle. Now, this is the problem of diversity. So here the two learned models are not diverse. They do not differ from one another. So they basically repeat the same information. You don't want to recruit two experts who have exactly the same skill set of expertise. Otherwise, like they will be doing the same job. You're wasting your money. So here the idea is I want my models to be diverse. So let's say I train a first model and I have a boundary like this, okay? This is my first model. And then I train another model, and this is my second boundary. And what do you guys notice? Somehow we have a very nice aggregational model, final model that finds the right boundary, okay, by aggregating these two decision boundaries. Now, because our models are diverse, the ensemble learner can outperform each of those models when they're trained independently, okay? So, right. Now, let's look at this. There's an important question now. How to generate diverse classifiers from whether a single classifier or multiple classifiers. Let's say you have a support vector machine, okay, or maybe, like a decision tree or a base classifier. So you have like a learner and you want to create an ensemble like this one, okay, different like models from a single learner. So here, model 1 is SVM, model 2 is SVM, model K is SVM. Okay, so basically you're using the single model, but you want to create different boundaries. So how can we possibly do that? So if you guys remember, this is just for a single, when using a single model. So let's say when using a single model, we have our training samples, the green dots and the pink crosses. And here, what we notice that we have a very complex, nonlinear decision boundary, okay? So finding a model that can nicely, delineate or estimate this boundary is using machine learning might be very challenging, okay? So in this case, what we can possibly do is there is one simple concept. How can we, use the same model still? And so let's say giving a data set X, okay? Using the same model, we create different, not using the same tool, like for example, SVM, we create different models. How can we do that? Different parameters. Very good. We can train with different portions of data. And this is what we saw in cross-validation. So when you're doing cross-validation, this is why you're building different models and their performances will be different. Their decision boundaries might be different because we're perturbing the data and creating different, folds of training samples. So here, this is the one way of creating the ensemble. So basically, we can simply split the data into different chunks. So let's say here we have, okay, now should be this one. Okay, so this is the first split of the data. Split 1. Okay, so this is my first training set, set 1, okay? And then I have another split, maybe around here, set 2, and set 3, set 4, and I can have other random sets like things like that. But to make it simple, I'm just going to keep this just these 4 examples. Then I will train my first classifier. So let's say I train classifier 1, model 1, and then if I train it on this set, I will get a decision boundary like this one. And then if I train it on the second set, my decision boundary will be around here, okay, to separate both classes. Then the third and the fourth set. So you can see that somehow I have started approximating these parts, right, by aggregating these models. So basically right here, by creating these different decision boundaries, if I put them all together, I can somehow build this this overall decision boundary that is very complex using what? Using simple linear trained weak models. Okay, so this is one of the ways of diversifying classifiers while using a single classifier. So we can also do this by diversifying we can also do the same thing, basically split the data into different chunks, okay? And then we will be training different models. So maybe here we can train soft perceptron, we can train another classifier like a second classifier like linear, SVM, etc. So we can diversify also we can build our ensemble using different classifiers, okay? So, but the easiest way, the most commonly used ones, is to stick with one classifier and try to boost it, try to improve its performance by diversifying the training sets. So here is basically the 3 dimensions or 3 possibilities on how to diversify a learner. Okay, how to diversify a learner. So we can think about in terms of decision boundary, or what we call also model hypothesis. So this would be diversifying the training set. So we can diversify the training set, change the training set. We can also, there are other options. So how can we create from the same model, derive different models or different boundaries? So first thing we saw, we can just basically randomly partition the data into different subsets, train the same model on each subset independently, build these bunch of mini models, and then combine all of them at the end, okay? Now there is a second way, and you guys can get that. So we can, what did we see in the previous lectures? Dimensionality, reduction, okay? Feature selection. So what we can do, we can give the classifiers different features to train on, right? So we're not creating a subset, we're changing what's inside the subset, okay? So we're changing the features. So we can use PCA, we can use filter-based or wrapper-based feature selection methods. So here we can basically change the features that we give to each classifier, okay? So this is the second way of diversifying it. The third way is what we call hyperparameters. So some classifiers, they depend on hyperparameters. Okay, so in SVM we have the constant. If you guys remember the margin, we set it to 1, +1, and -1. So this is actually a hyperparameter that we did not discuss, but by changing those hyperparameters, if there are any, you can also diversify the classifiers, okay? Now, we're gonna look at these 2 examples, the training set, 2 different ensemble strategies when diversifying the training sets, and we will look also briefly at the features, how does it work. So here, let's start by the feature diversification strategy, okay? So here's how it works. So generally, what we can have, as usual, we have our training data, corresponding training labels. then what we do, it depends whether we're using supervised or unsupervised feature selection methods, but we have a bunch of feature selection methods. Okay, feature selection methods. I will apply them. So here in this framework, the way I have schematized it, you can see that these should be filter-based methods, okay? Because, you know, they're like, they do not cooperate with the classifier. Okay, maybe unless if it's embedded in them, so maybe it's like inside this box. Okay, but for now, let's say for the sake of simplicity, we're using a filter-based feature selection method, and then we are using different methods. So FS1, FS2, FSK. So what we will do is the same thing. So very simple. We input the data to each of those feature selection methods independently. So we learn how to select different features using maybe PCA, okay? Then we give those features to our classifier to train it, okay? Then we use maybe infinite feature selection method. Right here, we give the top K ranked features to the second classifier, and we do that again using another feature selection method, give the new extracted or the new, you know, like, so here I made a mistake. What is the mistake that I've made? You guys were following? I said feature selection, and I mentioned PCA. PCA is not a feature selection method, it's a feature extraction method. But if I change those, okay, if I change those, and I write something like this, okay, dimensionality reduction, oops, okay, dimensionality reduction, DR method 1, DR2, so you can use a bunch of different techniques. Okay, great. So, right, and then after doing that, this is basically more, we can say this is more generic, okay? So you can include feature extraction and can be feature selection or feature extraction methods, okay? Now, after that, we train all these classifiers independently. You guys need to keep that in mind. So these models are trained independently. And in the testing stage, when we want to test, it's simple. So we do the same thing. So we have our test set. And of course, we don't have the labels, okay? So we give our test set to each of these models independently. And then what we'll have a final, we'll have a prediction from each of those models. So this test set will go through the dimensionality reduction technique, classifier, etc. And then ultimately, somehow, we will aggregate all of those. And this is the classifier combiner step, okay, aggregating all of those. So this is, you know, diversifying classifiers using different dimensionality reduction techniques.